That was really, truly beautiful. Thank you so much for that amazing introduction. I'm thanking you. In the following hour, I want to take you on a little round trip through the current fieldwork I am engaged in. I will give you a short introduction into the methodology and theory of the anthropological field, then continue with some insights about my current fieldwork, focusing on the institution I am investigating, then reflecting the influence of computer simulations and internet communication technologies on high energy physics and its production of cosmological knowledge about the nature of nature, in anthropological terms, our understanding of space and time. I started my research last October, and it is designed as a long-term field study with an overall time frame of about 2 to 3 years. The field. When I was turning into an anthropologist, I quickly got introduced into one of the most important secrets to the successful accomplishment of an ethnographic fieldwork. My advisor, the well-known German-European ethnologist Wolfgang Kaschuba, replied to me during a discussion, "Anyhow, you have to love your field." His remark has echoed in me ever since, and I have understood it over the course of time as something more than just a pragmatic sentence aimed to help me to get to know my field from the inside. Ethnographic fieldwork is an embodied method which lets you experience insight and confronts you with your own expectations when you deal with your informants and the collected information. Loving the field means learning to understand that science and the will to know are closely connected to desire. To observe a field means to learn about the will to know and the will to power displayed within the field in question. To grasp the meaning of this thought of loving the field might be one of the hardest tasks you are about to learn when you strive to become an anthropologist, because the field is something that affects you, no matter how hard you try not to be attached to or touched by it. Now, how does anthropology define the field? Anthropology does not know a consistent theory of the field, because method and theory are personally shaped and transformed during the empirical ethnographical fieldwork. In order to produce theory, you gather data in your field, let time pass and thoughts evolve. Then you slowly start to grasp the meaning of your experience. You get out of the field and the time passes again. And again, your thoughts transform experiences into insight until they will be written down and finally published. From this moment on, you are not able to change anything about the description of the field anymore. It became a function, an object of ethnography, created on the basis of fieldwork, of participant observation, interviews, field diaries, and source analysis. Anthropology borrowed the term field from physics and struggles with it. Like quantum physics has to struggle with a consistent theory of its field and questions the standard model all the time. Because within fields, some things are unsolvable, undecidable, incalculable, unpredictable, or simply incompatible with the standpoint of the observer. And as in quantum physics, we have to deal with principles of uncertainty. Sometimes we see aspects in our field which have to be described as disturbance, as oscillation, or difference. Like waves, words wallow in meaning. Discourses appear. The language is a sea of thought. Time and space get blurred here. We lose all the possibilities of measurement. But sometimes we are able to do exactly the opposite with the data of our field. We categorize, we cut up our observations, scale them, bring order and structure into what we record. Then, like particles, things assemble meaning. We can trace their jets as soon as we confront one thing with another. We position cases. We see the possible solutions for that which could be logically described because, as Ludwig Wittgenstein emphasized, the world is all that is the case. We search for the important aspects, detect discourses, seek structures, and follow traces. We need time for research because the analysis of complex cultural aspects demands time, is time critical. How can one measure the time needed to transform experience into insight? As in particle physics, anthropologists interpret properties of agents, relate and describe reciprocities, strong and weak interactions within the field. The field is something we make out of traces. We are constantly confronted with interferences and superpositions, deal with linearities and non-linearities, with continuities and rifts, historicity and ahistoricity. But unlike in particle physics, we still try to describe, although disenchanted and not naive, culture as a complex whole in which we take part. This means that we have encouraged to describe all aspects of the field we study and reflect our impact too. We have to take into account the raw and the cooked, the cold and the hot, the coherent and the ephemeral, entropy and order. The anthropological field is, by its empirical constitution, something that is the case. By its epistemological framing, something that is coming into being. Like my new research field, the field of quantum physics. I found this field while I was searching for answers to problems I had with my last anthropological field, where I did research on the relationship between language and identity with reference to Austrian writers and the German language. It was summer in Vienna. The days were made out of steel, like Ingeborg Bachmann would say. I sat in front of my desk and read. My field was gone. All writers and creative artists who I intended to interview were somewhere outside of the city within the realm of the Danube, gone to the Sommerfrische. I had lots of time to think. Participant observation, anthropological fieldwork seemed to me in that moment as something like an old car which needed a new chassis. Cybernetics had not been enough. Edward network theory did not help further, and the work of Gilles Deleuze made me perceive rhizomatic and transversal discursive structures everywhere. Media theory did not enter the scientific discourse of anthropology yet. Something was wrong with the conception of space and time within participant observation and fieldwork. Somehow, anthropology did not take up its task in order to position the ontological, philosophical within its own method and theory. I was overwhelmed and I felt I pushed myself too hard into entering the field. I needed answers. And where else would I look up as on the other side of Wilhelm Dilthey's Rift Valley? In quantum physics, where you have a massive observer situation going on. To round up, my initial interest in my new research field was purely for theoretical reasons concerning the conceptions of anthropological fields. Now, how does this influence the field I am currently studying? How does this shape the way I am observing my field, where I am following the question how data gets turned into cosmology, how ideas of space and time are constructed within quantum physics? And why do I tell you about these moments of my last fieldwork? The reflection of the path to my new field helps me to understand where I am not the field, helps me to observe and keep distance within the field. Every day I am in it or out there. This neither prevents nor hinders me from falling in love with my new field as I did with my old. And I started to love it from the very first moment. And one thing is for sure, I will never be able to go native because maths matters too much. And I have this phantasma which is called language. Once you enter your own field of research, you gather data encoded in words. But the data is not to be trusted. Words are promiscuous. They grant everyone their own distinct meaning. Therefore, the gathered data needs to be tamed by constant verification, systematization, and dissection. The exceptional needs to be extracted from the usual. Only then are common sense and everyday life forming within the field. Humans are, in ethnography, not just a number within the whole equation. Computer simulations are something we cannot use in our field. Imagine a piece of software which would allow us to calculate all different historical, social, cultural, natural, and technological parameters. We, social scientists and members of the Club of Humanities, are not able to simulate a field because our expectations are nothing but prejudices. Our ignorance hinders us to say anything before we gather data. We can make up theories. We have some serendipity where our field might be leading us to, but the rest is full of accidentality and chance, which cannot be simulated by a stochastical program. Because unlike in particle physics, our cosmos is not made out of numbers, waves, and particles, but of things, words, and all forms of togetherness and matter. And words, as human encounters, are incalculable, unpredictable. As soon as we enter the anthropological field and the realm of words, we leave everything that might be considered pure nature. And all watches stop. And the space of memory and oblivion becomes visible. A space where watches do not do their work, and we became part of the gay science, as Nietzsche emphasizes in his paragraph Against the Laws. From now on, time hangs by a hair around my neck, suspended there. From now on, stars shine randomly, sun, rooster, crow, and shadow flee. Whatever brought time to my mind, that now is mute and deaf and blind. All nature still in me, it balks at ticking laws and ticking clocks. About scientific economies and the cosmos. Quantum physicists have similar problems concerning their scientific habitus and milieu, as well as concerning questions about their research, more specifically when they do research about time and space in our cosmos. They simply want to know, but hello, they may create black holes, which could be one of the explanations why their science is so much more interesting than ours. Or, as Sophie Houdin puts it, I quote, "As a potential site of the drama, the Large Hadron Collider in CERN is subject to extremely close scrutiny, extremely careful measures. By equipping itself to tirelessly document the minuscule, the Large Hadron Collider picks up more of the noise of the world than it needs. From being a place vulnerable to big disaster, it becomes a place through which danger becomes perceptible in its smallest aspects of whatever nature that danger may be." End of quotation. From the beginning, physical research was much more dangerous but also cost-intensive than our experimental systems like participant observation or even hermeneutical reasoning. We are relying on time. We do not need expensive machines and materials when we are analyzing our research interests. We need time to do it, and time is money, but that is another issue. And I am convinced that the perception of space and time is something which evolves and can be transformed, and it is time to come to another perception, because who is not moving with time will be moved away by time. Everybody knows the eternal spatio-temporal questions concerning our being within the cosmos. Where are we coming from? Where are we going to? And what is holding the world in its utmost form together, to quote Faust from Goethe. But how can you turn thoughts like this into money? As you see, like religions, quantum physics actually found a way. They know how to do it. They follow those questions in dealing with nature and phenomena which are unpredictable, relying on presumptions and theory. Through maths and experiments, models, technology, teamwork, and vision, they produce knowledge about space and time, which seems to be much easier to turn into money than the knowledge of the humanities. Although the Big Bang theory is something quite young, and quantum mechanics as well as relativity theory are something impossible to understand for most of the human beings, researchers are able to gather billions of euros for their research. How do they do that? And what is in their discourse that seems seductive enough to attract billions of euros every year? They are telling us about the nature of space and time, unveiling the fundamental laws of nature, shaping our ideas of nature and the cosmos. But is it true? Or is it a cultural program of thought which is inscribed into philosophy and shaped by media and techniques? What impact do media have on that knowledge? What is it they tell us? What can we learn from them in order to understand our own reasoning? As an anthropologist, I do love my field, but this does not mean I trust it. My field is something that unveils different historical, ontological, and cultural ideas of the present. My methodology allows me to describe contemporary phenomena. When I look at the CERN, I see emergent forms of knowledge through participant observation of the place of knowledge production. This scientific institution tells a story about its society and their beliefs because it is filled with humans. And the society which constitutes the CERN is transnational, globalized. It happens to be my own society and my own world, which constitutes the CERN. I am involved in what I'm observing. What I see is a transnational community, highly culturally differentiated, which tries to come together in the language of numbers and some really awkward English, and which transcends all particularities into the beginning of our cosmos, shortly after point zero, around a trillionth of a second after the Big Bang, building a gigantic Tower of Babel that would work this time. One does not have to go very deep into intellectual history of the Occident and the Orient in order to understand that the search for the origin of the cosmos done at the CERN seems to be, from that perspective, something quite obvious, even natural. It is the ultimate quest for oneness that one can trace in all monotheistic religions and as well in Attic philosophy. And there are reasons why this kind of quest to seek the origin is situated in Switzerland, both the idea of origins itself as well as quantum physics of high energies have historicity. And it is out of simple historical reasons that the research about the origin of our universe is done at the heart of Europe, why it is CERN where particle physics is used for peaceful purposes. Insights into particle physics have been already for a long time been pushed and instantaneously used for military purposes. And CERN, as an institution designed for fundamental research, tries to leave its origins behind it. In fact, Everything that is in use right now at the CERN can be somehow traced back to the history of military projects, like the Manhattan Project or the research done at Los Alamos scientific laboratories. High-energy physics is based on mathematical computation and carries out mathematical experiments. Without the innovations of the computer, operational research to master air war, or even the internet itself, CERN would not exist. And today, some of the detectors, which you would see later, carry some parts of Soviet submarines that aren't in use anymore. What happens in the detector of CERN? In the following paragraph, I want to give you a short introduction, quite technical, of the research institution and introduce you to my current research about the biggest machine that was ever built by humans, the Large Hadron Collider at the Centre de la Recherche Nucléaire in Meyrin, Switzerland. Since 2008, beside other particle accelerators, CERN has hosted the Large Hadron Collider. What does this mean? Like many effective physical experiments, first of all, it means a very simple and aesthetic experiment. Two particles collide. I quote the CERN collaboration. Inside the accelerator, two high-energy particle beams travel close to the speed of light before they are made to collide. The beams travel in opposite directions in separate beam pipes, two tubes kept at ultra-high vacuum. They are guided around the accelerator ring by a strong magnetic field maintained by superconducting electromagnets. The electromagnets are built from coils of special electric cable that operates in a superconducting state, efficiently conducting electricity without resistance or loss of energy. This requires chilling the magnets to minus 271.3 degrees Celsius, a temperature colder than outer space. For this reason, much of the accelerator is connected to a distribution system of liquid helium which cools the magnets as well as to other supply services. Thousands of magnets of different varieties and sizes are used to direct the beams around the accelerator. Or, as one of my informants said, the whole Atlas detector was built to prove one theory from the year of 1973. Now, what do they exactly do at the Large Hadron Collider is simulating the Big Bang on a tiny scale. The traces of the event of collisions are recorded by detectors, such as the Atlas detector. Like the other three detectors, Atlas measures the characteristic quantities of physical magnitudes of particles, which are generated through collisions. The measurements are based on computer simulations of events that were conducted before. In fact, the detectors are embedded, surrounded by one gigantic computer simulation. Otherwise, the computer would not know which information it would have to record. What do they record at the detectors? The observables, of course. The measurement of the impulse of charged particles within a magnetic field, the measurement of energy of charged and neutral particles, as well as the measurement of the total energy of all generated particles. The definition of total energy seems to be important in order to detect new types of particles which do not interact with the detector and leave it without depositing energy within the calorimeter, like neutrinos or light supersymmetrical particles. The production of such a particle shows itself in an uneven impulse energy and result of the event. Atlas was built to detect the Higgs boson. Supersymmetry and dark matter get investigated here as well. Furthermore, the smallest particle of matter, such as leptons and quarks, are analyzed for possible substructures. In order to validate and prove the experiments conducted at Atlas, there is a second detector at the Large Hadron Collider called CMS, and they are in a competitive mode. They are trying to answer the same questions with another physical approach. I quote again the CERN collaboration. For each collision, the physicist's goal is to count track and characterize all the different particles that were produced in order to reconstruct the process in full. Just the track of the particle gives much useful information, especially if the detector is placed inside a magnetic field. The charge of particle, for instance, will be obvious since particles with positive electric charge will bend one way and those with negative charge will bend the opposite way. Also, the momentum of the particle, the quantity of motion, which is equal to the product of the mass and the velocity, can be determined. Very high momentum particles travel in almost straight line, like the muons. Low momentum particles make tight spirals. About the influence of computer simulations. When you accelerate particles, you can let them collide. When you make them really slow, you let them interfere. That one physical phenomenon behaves according to time and escapes our dimensions at the same moment is one of the truly ungraspable and strange wonders of nature. That we are able to describe it with maths, reproduce it with techniques, is a wonder of culture. The capabilities to experimentally show it is based on technology and its means. In order to generate and analyze data, physicists have to fuse abstraction and concrete design, words and math with the things and matter. And a detector like Atlas consists out of many technical parts and programs which are all designed by humans based on fundamental laws, possibilities and principles of nature. As you might see already at this level, computer simulations are inseparable from the experimental system, because the detection and even the construction of the whole thing needs lots of theory. Not only quantic theory, but also simple mechanics and thermodynamics, and many calculations have to be done in order for this machine to be working. The Atlas project alone is the host for 3,500 workers within knowledge production. Most of them write algorithms. Without computer simulations, high energy research about particles could not take place. There are theoreticians at CERN who program Monte-Carlo generators, which means they calculate models of probability. There are people who design configurations for programs which are used for the production of simulated events. Another group, the Monte-Carlo production group, coordinates and manages the production of different simulated data samples and settings on the Atlas grid. And then there are groups of physicists who analyze data by modeling, coding parameters and variables, who do actually simulations, write articles in order to get published. The final goal are consistent histograms. Analysis consists out of algorithmic models in order to calculate the limits of an event. To differentiate signal from background, to calculate mass weights, to build a model of comparison, to exclude assumptions, and to find certainty by relying on systematic uncertainty. This process affords several highly specialized, high-energy physicists groups. The position of the experimenter mediates between simulation and event. Monte Carlos are the basis for research on particles at high energies. The simulation is a tool of scientific comparison. The real deal with computer simulation starts in the moment of unblinding, to say it in native speak. Because just when the simulations are not corresponding with the collected data, as you can see here, we can talk about new phenomena and find a way that theories get proven. At the end, all layers of computer simulations contribute to an understanding of the value and the truth of the data. They are the control plot, algorithmic alter egos of the materiality that is shaping the detector and what it records. It all serves to understand nature smaller than the size of a proton at energies that supposedly happen to exist 1/1,000,000th of a second after Big Bang. So, what is the real meaning of computer simulations at Atlas? As one of my informants said, the whole detector is built into a gigantic computer simulation. In other words, what we see in the picture, what we touch there when we visit the CERN, is the earthly core of a virtual network of a gigantic hypercomputer. And where is the position of humans? I quote again one of my informants. The position of the human is right in between the computer simulation and the events taken due to the run of the experiment. He has the position of analyzing, and that position no computer could ever take. End of quote. Between nature, the detector, and Monte-Carlo simulations, the experimenter is the only one who is not behaving according to the stochastic episteme. Peter Gallison writes, I quote, "The Monte-Carlo and the computers that gave it power did much to bring cohesion to the scientific community, but only by establishing trading zones between otherwise highly disparate groups. It was a cohesion based on the establishment of a locally shared culture, a cohesion far from a Comtean dream of a hierarchical tree of knowledge." End of quotation. This has been leaving its imprints on the scientific community until today, shapes the trading zones and gives birth to boundary objects they are dealing with, the particles. To summarize this paragraph, in order to gather knowledge about particles, computer simulations are used on all levels of scientific reasoning within high-energy physics. The models which serve to detect the events within the collider are based on computer simulations. Monte-Carlo simulations are used to calculate probabilities of the known in order to differentiate the unknown from the event of nature. There are groups who even look for the unknown within the unknown, although until now they did not find anything new. How should they trace something new when they use an experiment which is by its constitution half a computer simulation anyhow? The data and the event are both a palimpsest of algorithms. Probabilities of quantums are at stake. How are probabilities relating to truth? For the majority of particle physicists at CERN, observation of their objects of interest are not something highly mediated or culture-bound. They are convinced that they are observing nature as it is. Standing on the top of a giant named Occidental science, here people are aspiring to detect truth. And the truth they are able to sell at the end of their research, like the detection of the Higgs particle, is something that has to be negotiated. Truth is here something that lies within time, as Kierkegaard already remarked. And not only humans are producing this truth anymore, they are relying in their observations on technical conditions, on computers and other machines. And these conditions are configuring our perception, shaping our ideas and framing our knowledge, therefore pave the way for forms of power. As much as the horizon of insight is widened by, for example, computer simulations, as much we are able to predict and detect the behavior of nature by the mixture of statistics and stochastics, still accident and lack of certainty are in sight. Can we trust computer simulations? What ideas of space and time are produced when you use a computer to gain insight? In order to find answer to that question, I study my field. What I see at CERN is something we do too: reconstruction of traces. The computer simulation reminds me of the systematization of sources accomplished by one of the founding figures of German historiography, Johann Gustav Droysen, who was separating in Tradition and Überrest, tradition and what is left over or leftovers. We find within the archives tradition, which would be the generation of events. We seek for leftovers of culture, the unintended traces, like astroparticle physics, for example, searches for particles from the Big Bang who still remain until today. But the traces physicists reconstruct are shaped and modeled by computer simulations. As a CMS physicist states, I quote, "The Higgs boson would decay instantly into lighter particles. We only detect these resulting particles, so we have to be like detectives, look at the evidence to see what happened," end of quotation. What happens when the detectives create their own case? In this case, a field of particles. To me, physicists finally arrive with their computer simulations within the realm of history. They deal with similar problems of generating, preserving, and structuring their objects. They even enter a similar discussion about space and time, although most of them do not think about that kind of stuff. What I learned already in the beginning of my fieldwork was the widespread conviction of physicists that nothing is certain, and that nearly any theory can be questioned, besides some holy cows, as they say, such as Newton's universal law of gravitation. The algorithmic production of evidence with computers is one of the main subjects of media theory. Simulation is a word which is related to simulacrum and simulatio in Latin. It is traceable to another simulated origin, the Indo-European. It is traceable to the word root sim. Simulations lead to the similar of the one, to something that resembles, dem Ähnlichen, which carries the Ahnen, the guessing of something else inside itself. The simulo signifies the mimesis, the simulation of something. It transforms the cases of the world, is in itself already manifolded and fractal. Another word to which the word simulation is related in Latin is jealousy, which was named, besides zelos, also simultas. Simulations compete with reality. They prevent paradises, they tackle the future, they simulate the simultane. Tensions and reciprocal interactions of different states of what could be the case are created, generated through simulations. Different experiences of time and space are meeting within the observer, because the simulation leads to the collapse of the frontier between things and events. As a result, something new comes into being and leads into the simile, the similarity of experiences, relativizes and objectifies reality. There lies virtue and vice of computer simulations. The simulation warns us not to trust any feigned experience through pretending insight with simulation. Experience, experiment, and insight have to be kept at a distance so that we grasp a symbolization of nature. We can only characterize the events and detect the fakes, no matter how much we are erring and failing. While we are doing it, knowledge is time critical, and so is truth, something which is related to a specific environment. As you might see, I'm entering with my field a difficult realm of uncertainty. What does nature mean? What is culture? What role does the medium play in mediating nature and culture? And is the medium not the epitome of nature culture? Shouldn't we talk of nature culture? What is particle? Is it matter? Is it semiotics? Is it a material semiotic object, following Donna Haraway's reasoning? Somehow, the observations of the 20th century in the natural sciences influenced the vocabulary of academic English. Word couples are created. Oxymora enter the scene of representation. Nature culture, space-time, material semiotic, raw data, participant observation. The lines between logos and physis are blurred, and sound as well as light becomes something that is an algorithm and at the same time part of our daily construction of meaning. Epistemologies and ontologies are hard to grasp through empiricist research. In order to reach my goal, I would have to follow an ontographic approach, as Mike Lynch would put it, in order to investigate the production of things. This allows me to describe, I quote, genealogies in Foucault's sense and weave into my research the historicity of discourses, like architectures or economies, which are the framework for ontologies. In order to describe this phenomenon, I would require, I quote again Lynch, agnosticism toward particular positions in disputes about matters of concern, end of quotation. I could then provide an orientation to how matters of concern, as well as matters of fact and questions of identity and difference, are composed and invoked by the informants of my field. And this encompasses the possibility that my interest is not intrinsic to the field, because, let's face it, most of the physicists until today just shut up and calculate. But they do this within a team, and for that they need communication technologies, which brings me to my next paragraph, because these situations are the door openers of my field. Because my field is everywhere. Like here, Humboldt University Berlin, Adlershof, natural sciences area. I walk through university floors and enter rooms where people sit and work. Like this guy. You know that from your own work. My position is behind the scientist in this case. The scientist will meet his colleagues in a virtual space using a software called video, designed in close collaboration with the CERN. So this is another picture I took at the CERN itself from open video. And what you see here is the software, the interface of the software. The green dots are the people who are in the room right now, who are part of the group I'm studying at. And on the right side, you see the common chat where they all can talk about. In the middle, you have the chance to show videos. And behind there, you see already the most important tool for their reasoning, the PowerPoint, which brings everybody together. And what you see here as well, I had to black mark everything. What you see here as well is they have a very tight and very well organized schedule of doing their research. They have to bring 12 people together. There are always in a group 4 people who are doing nothing but asking stupid questions or not stupid questions and really try to enhance the process. There are 2 group leaders, and then there are the workers, usually postdocs and docs, who are writing the algorithms and producing this complete simulation, a complete simulation of a possible event that never took place. And at the end, what they do as a work becomes a publication, and it will be fitted into the Atlas detector when when it's running the next time to detect exactly that kind of Higgs boson they're looking at. So, without the use of internet communication technologies in high energy physics, no knowledge production could take place. Since its beginnings in 1949, the CERN is a test ground for communication and information technologies. As you all know, World Wide Web and HTTP were initially designed for the CERN, corresponding to the needs of interdisciplinary scientific exchange demands. In order to produce knowledge as CERNs, ICTs like video or its predecessor EVO, which when he was debugged was sold, the worldwide Large Hadron Collider computing grid, or simply a program like PowerPoint, serve a complex process of synchronization of space and time, connecting people, helping to exchange information in different social gatherings, mediate and generate data on a technological level. There are formal and informal group meetings which help to clarify thoughts in a secured space. Bigger formal meetings which show the process of negotiation in the bigger science community, of which the majority are working for the detectors. As stated in one advertising video of the video company, the video program and the CERN have a relationship. But what happens when the relationship has a problem? What happens when the relationship has its difficulties due to constant breakdown of the program? How do ICTs structure and govern communication? Several layers of time regarding aspects of human knowledge, media, machines, data have to be arranged in order to guarantee knowledge production within team-oriented science. Constantly, people have to operate with differences and help to establish a successful transmission of information. Some of the techniques which are applied in everyday work practice, like for example the use of the slides in PowerPoint and the coordinated and hierarchical exchange between different disciplinary trained and highly skilled differentiated scientists, can be traced back to military research during World War II, as I reasoned already. The CERN profits from that formation of a flat hierarchy organization of knowledge production until today. The group I study, for example, currently writes an article about a specific Higgs boson beyond the standard model. For that reasons, all important informations are gathered in a tricky page from articles of a group organization, over protocols of every meeting and a common LaTeX document which has to be updated with the progress of the group. With every change in coding and training the data, the common LaTeX document will be changed too. Email exchange and group discussion serve the coordination of knowledge. This tight and multimedia structure causes a dynamic of production which leads more or less effective to results. Every member of the group has access to the internet and the tricky page where everything is stored in different repositories, and some of the group who attained a special certificate are authorized to write the newest aspects of the work into the common tech file. From a participant observational point of view, recursion and reciprocity of communication content and technological form are obvious through, I quote Irina Kaldrak, dealing with data. And the anthropological observation helps to address current problems of modern contemporary work life. Time is a linear loop leading to a product, in this case, a publication. With and within the use of internet communication technologies, the present gets a completely different meaning. Here, past and future are at stake. Data, memory, is a digital stock of data, which is constantly transformed by the agency of the physicist within a complex web of coordination from the micro up to the macro level, from the quantic to the local to the global, even to the cosmic sphere. What fascinates me about this whole field the most is that the same tool of thought which secures the method of transmission on a technological level, redundancy, as Paul Baran stated, is also visible on the rhetorical level of discussion, mediated and reinforced by ICT software. Audiovisual chat rooms enhance the repetition of thoughts and intensify, sometimes prolongate and deteriorate discussions. But exactly this erring helps to find the common goal. What produces the value of an information, as Wendy Chun stated here, in information technology is repetition. Constant pinging defines the object, leads to identification and unambiguity. And what I observe is that this structure repeats itself in the communication with ICTs as well as team-oriented knowledge production. The World Wide Web is based on the polygamous HTTP protocol to transfer big amounts of data through a distributed network. Both were invented initially for research purposes at CERN. The audiovisual communication software video exists in order to establish and secure knowledge production promiscuously as well. It distributes, disperses, discretizes. Its impact needs to be mediated and negotiated by the people who use it. The disidentification on the technological level precedes identification. The software itself has an important impact on the way people discuss. Instead of Aristotle's assumption that cause and reaction are always happening at the same place in time, causal reactions happen at two places at the same time, on the technological level of the hardware over data transmission, as well as on the level of communication with software like video. But there is a problem. The video program, for instance, is full of bugs. It constantly breaks down and causes difficulties of communication. Billions of emails to CERN direction did not change anything. The software applied interferes with the data. Considered analytically, the but helps to understand the power structure of the medium. From a media theoretical point of view, one can state that as long as the machine runs, one does not realize how it works. As soon as the computer has hung up, the machine becomes visible, and with this interruption of simultaneity, the power structure of software and hardware unfolds to the observer as well as to the user. And usually it is that moment of breakdown and bugging which causes frustration and aggression within the group against the program, and due to my observation, helps to distract from the intergroup communicational problems. This is a form of displacement. The techniques or the problems with the data are helping to stabilize the group identity and construct a drive for striving to reach the goal. To sum up this paragraph, on the communicational level, one can see the same problem as on the level of the medium itself. The securing of transmission of information in order to produce knowledge is secured by redundancy. One can observe constant loops of discussions which lead at the end to a knowledge product like an article or a particle, an event or a statement with impact for the scientific community. It seems to me that it is exactly that constant failing and repetitive redundancy, being even stronger due to internet communication technologies, which produces new knowledge. The iterative way of discussions and the discrete way of storing data influence reciprocally the production of knowledge and reshape it. The media not only mediate the process of knowledge production, but have an agency which influences the uses and the outcome of everyday work practices. Truth itself becomes here something that lies within time itself and needs constant negotiation. Behind all the use and development of ICTs for high-energy physics lies predictions about the meaning and the possibilities of the detection of the everlasting, eternal truth of nature. This highly symptomatic culture-bound hope to seek and find final truth within an interplay of probability and data that is generated by digital systems which rely on computer simulations pushed the production of ICTs in the first place and has been enhancing the possibilities of computer-based communication until today. To end my presentation about my first research results and attempts to analyze, I want to draw your attention on one last thing concerning the object of quantum physics, particles. With the help of detectors, high-energy physics are able to observe the behavior of particles inside the atom. But the event high-energy physics are observing is something that is accessible for them just via retrospective observation and with the help of computer simulation and artificial experimental generations of collisions. Physicists gather data, track events, but nothing they observe could be defined as a fact, although it is presented as such. They see jets, processes, and enter the realm of historicity. Hermeneutics in science starts when computer simulations are in use. And like peasants, these historians of science are entering their barns, creating and taking care of their archives and discuss with the help of their tools within a huge group their observations. Particle jets and particle showers are analyzed within the field. Histograms are always in use. Isn't it funny that the term particle zoo was coined for the muons, gluons, and everything else that is even inside of us, because we are made out of atoms? What does this metaphor imply? Are physicists still believing that they observe tamed and imprisoned versions of nature? Or are they capturing nature like hunters? They themselves would object. For them, particles are something to be arranged pragmatically. What counts is getting insight, proving or disproving the consistency of theories with the help of machines. To follow this desire to know is the only true aim to do research. And as it has been commonly known since Foucault, knowledge and power are inseparably aspects of will. The more physicists know, the bigger their willpower and desire for power. At CERN, not only cosmology is negotiated, also forms of community and dealing with knowledge. While the physicists tackle the frontiers of our knowledge about the nature of nature, they are shaping the landscapes of knowledge. For their knowledge, computer simulations are essential. Media are key and lock to understanding of the fundamental conditions of being within the world. Data memories and save media, data memorizes and saves media have an impact on oblivion and memory. When the software or the hardware gets outdated, the data gets lost as well. Even within new media, the dream of a complex, endless memory will stay a utopia and not fulfilled. Memory stays something fractal and fragile, but high-energy physicists are working on data preservation today as much as they work on middleware, which connects computers via grids and enables this kind of data preservation. That is why you have to take into account for an ethnography about knowledge production in high-energy physics, hardware, software, and the research collective. The hardware sets the fundamental conditions and restraints of the apparatus of insight. The software, because it calculates the parameters which are detected, tracked, and recorded, and it mediates. The decision makers for the calculations of the parameters and the building of the machine, a research collective which keeps the whole machinery going. Even if the machine takes away the famous man-hours of John von Neumann, the very same machine asks for man-hours in order to program and code algorithms. In high-energy physics, informatics is used every day. But the CERN physicists are no computer specialists. They are, as Johannes Lehnhardt says, I quote, without status of expertise in machine language. Therefore, epistemological and technological aspects are interfering. And it just happens to be their tool. And they deliberately acknowledge that they deal with informatics as they deal with mathematics. Sometimes they simply use abbreviations. The divergences which would be coming from that cannot be found anyway. These solutions, in order to have a neat histogram, appears well in the calculations within the Newtonian physics and the calculations of spaces and tuples within quantum mechanics. On the subatomic level, statistics and systematic errors are produced and computers help to solve the complex equations. Many physicists I interviewed remain skeptic toward the medium they use for their knowledge production. This skepticism is at the same time the main drive to ameliorate the software and the machine and to diminish systematic and statistical errors. It needs thousands of failed computer simulations in order to come to coherent simulations of a process. This path of erring and failing is part of the research process. The detector of events which simulates nature are embedded within a gigantic simulation, and reciprocally, the gathered insight is shaped by computer simulations. Approaching models, make models more coherent and better is one of the main tasks at CERN, using equations which are hypotheses about the nature of nature. Some of them are validated, others may never will be. Knowledge about space and time has to stay necessarily undetermined and endless. This condition of knowledge is like the idealistic and utopian mirror of human collectivity, because each of us is finite, determined by so many circumstances. We have to have space where our hope to arrive one day at a goal stays never fulfilled. This conception of knowledge merges perfectly with the current economy, which is designed to produce constant growth, i.e., which is always in lack of something. A cosmological theory like the one physicists design about the nature of space and time stays necessarily endless, because physicists are able to simulate a Big Bang, but with their means they will never reach point zero. It will always be uncertain. And that is part of the eternal condition of the humane according to the culture and its Indo-European language in which the CERN is embedded. A condition which is neither chronological nor topological measurable, but belongs to spatio-temporality where future and past interfere with present times and origin becomes a trace. Thank you.